very much. So I want to, first of all, thank the organizers for the kind of invitation to speak here. It's a pleasure to be in NORDITA. So I want to talk about this work in progress, but hopefully to appear very soon, probably next week, with my collaborators Vincent Caudrelier, Derek Howland, and Anup Singh. So where we derive some variational formulation of the Hitchin system. So I'll explain the subtleties in that statement. And to start off, I want to first give some motivation for this work and for this talk. So it's in the context of this general correspondence, which was initially formulated by Costello and further elaborated by Costello, Hitchin, and Yamazaki, between integrable field theories on d-dimensional spacetimes called M, and gauge theories in two extra dimensions living on the product of the manifold M and a Riemann surface C, which are holomorphic along C and a mixture of topological and holomorphic along M. So the heuristic motivation for this correspondence is basically that underlying integrable field theories, you have a lax connection, which is a connection that depends meromorphically on a complex parameter. And so what the gauge theory does is it incorporates this complex parameter as part of the geometry. This is why you have this extra factor of the Riemann surface. And the idea is that the gauge field of the gauge theory becomes this lax matrix, which is inherent to integrable field theories. So there's been a lot of examples of this general picture in various dimensions. So the first one was this 4D Chern-Simons one on a two-dimensional space-time product with a Riemann surface. And this corresponds to two-dimensional integrable field theories on the two-dimensional space-time. So I should say that, well, this was first of all initially developed by Costello and Yamazaki, and then later by lots of people. And it's really mostly been understood in the context of the Riemann sphere and also elliptic curves. So we've seen in the previous talk some examples of elliptic integrable models, and they fall in this category. So these are 2D integrable field theories, so string theories fit in this column here. And because the world sheet is two-dimensional, and elliptic deformations are those where the Riemann surface is the elliptic curve. So there are also high generalizations, which I won't talk about at all today, but they are all mostly understood in the case of the Riemann sphere. We don't know much about high genus Riemann surfaces. And the point of today is I want to go down in dimensions to 3 dimensions, where there's this correspondence between what's called 3D mixed BF theory on R cross a Riemann surface and Hitchin system. And the reason I want to go down by 1 dimension is because the Hitchin system is a very beautiful and rich integrable system, which can be formulated on any Riemann surface of any genus G. So in particular, this correspondence, I will explain how it really works on any genus. The Hitchin system is an example of a completely integrable system. So there's a whole hierarchy of Hamiltonians part of this system. And so the aim of the game will be to describe a Lagrangian for this hierarchy of integrable systems. And the other thing is that we're able to actually derive a 3D mixed BF theory from considerations of the Hitchin system. So usually what's this story, what you do is you start with a gauge theory, and you fix the gauge, and you end up with an integrable field theory. So what I'll show here is you can actually think carefully about the Hitchin system and realize that actually it's described by 3D BF theory. So you go the other way. Okay. So let me start by describing precisely what I mean by a completely integrable system. So I am assuming not everyone here is familiar with this. So let's take an n-dimensional manifold. And if you consider the cotangent bundle and you have a Hamiltonian on this cotangent bundle, the dynamics induced by this Hamiltonian is called completely integrable or Liouville integrable if there are n functions on the phase space which have the following 3 properties. So they have to be conserved, meaning that their Poisson bracket with the Hamiltonian should be 0. The crucial property as well is that they are in involution, which means that they Poisson commute with each other. What this means is that the flow induced by any of these Hamiltonians, I call these Hamiltonians, they preserve all the other Hamiltonians. So in particular, what this tells you is that you can restrict to the constant level surface where you fix all these Hamiltonians to constants. So this describes a Liouville torus within the phase space, and the dynamics holds on these Liouville tori. So this is the notion of Liouville integrability. And crucially, we also ask that these are independent integrals of motion, of course, so that they're locally, their differentials are linearly independent. Okay, almost everywhere. So you can always find an obvious integral of motion if the Hamiltonian doesn't depend explicitly on time. The Hamiltonian itself is conserved because it Poisson commutes with itself. So H1 is usually taken to be the Hamiltonian, but the key point is that these second two properties, they are completely symmetric in HI. So they're not sensitive to any particular choice of HI. So in fact, all these other HIs, they equally define integrable systems on the same phase space. And so the integrals of motion of one system define also flows which are integrable in this precise sense on the same phase space. So it's very natural from the point of view of integrable systems to consider all these flows together. So we talk about the integrable hierarchy of the flows. Okay, so you think about all the systems together as one, and the key property is that these flows commute because of this involution property. Okay. So the question I want to ask today, because the title is about variational formulations, is how do you formulate this intrinsically Hamiltonian property that the Hamiltonians commute? How do you formulate it variationally? So this was answered in 2009 by a paper by Loeb and Nijhoff. So they introduced this notion of Lagrangian multiforms, which provides a variational criterion for integrability. So to motivate this story, let me start by just considering one Hamiltonian and remind you how you formulate that in a Lagrangian setting. So let's fix a particular I and look at the evolution of the phase space coordinates under this time ti. So they're governed by these Hamilton equations for the Hamiltonian Hi. And these are encoded variationally in the first order Lagrangian given by PQ dot minus Hamiltonian. Okay. So really, this is a Lagrangian for a curve in phase space. So the curve is parameterized by the time ti. And the action for this Lagrangian, if you vary it with respect to P and Q, you find the curves which are critical for this action. Okay. And crucially here, I insist that there's no sum over I. I'm really considering one time for the moment. So it's the Lagrangian Li times dti. This is a one form which you can integrate over the real line. Okay, so the question is, how do you consider all of these independent systems together as one? How do you formulate a Lagrangian that encapsulates all of them? And crucially also, how do you ensure that the part of the dynamics is that the Hamiltonians Poisson commute? So you want this involutivity property to come out variationally as part of the dynamics. So the idea of Lagrangian one forms, which dates back to Loeb and Nijhoff and has been developed by many authors since then, is to introduce this notion of Lagrangian one form. So I'll be using a very recent reformulation of this language, which is due to Caudrelier and Harland, where they, for convenience, they introduced an extra copy of Rn, which is to treat the times on an equal footing to all the phase space coordinates. So this is just for convenience. You can do this without that extension, but it's nice to do it in this way. So in that case, you can write down a Lagrangian on this extended phase space where you have all the times as extra coordinates. And rather than thinking about individual curves in that space, because that would describe one particular system, you want to consider surfaces in that space, right? So you want to consider immersions of Rn, which are, Rn is this multi-time space parameterized by the different times. And you want to consider immersions of that into the target space. So you're describing a family of n different flows. And okay, so you take this Lagrangian one form on the T star m cross Rn. You can pull it back to Rn, so you get a one form on Rn, which is essentially what's in bracket here with the extra duj. That would be a one form on the Rn. But this is still a one form on the Rn, you can't integrate it, so you have to make a choice of curve, a smooth curve in Rn, so that you can pull back your one form on Rn to the curve and integrate that along the curve. So there's an extra choice of a curve to make. And the point is you get not just one action, but you get a family of actions for the degrees of freedom which are encapsulated in this function sigma. And the family of action is labeled by this curve gamma. Okay. So important to think that to realize that there are two functions involved. There's a curve gamma and there's this immersion sigma. These are on a very different footing. The curve is just an auxiliary curve probing this space of multi-times, whereas sigma is a function in the target space, in the phase space that encodes the dynamics of your variables with all these different times. Okay. So when you vary these actions, so you have to vary them for all values, or for all curves gamma. So you find the critical points with respect to sigma for all gamma. So that means you're varying with respect to p, q, and t. You get these equations here. And if you look at the last one, you notice, so varying with respect to t, you notice that if you substitute the first two into this equation, you basically get the involutivity property, except there's this Jacobian, so this matrix dti by duj, which you'd like to invert. Okay, so the key point is that this is possible because of the first two equations. If you look at the first two equations, if this matrix was not invertible, it would have a kernel, which would mean that dq mu by duj would also have a kernel, and so would dp mu by duj. And therefore, this differential of the immersion would not be injective. Okay, so that means that this matrix is in fact invertible by the assumption that this sigma is an immersion of an n-dimensional space into the cotangent bundle. So by inverting this dti by duj in every equation, first of all, we get the involutivity that we wanted, and we get the Hamiltonian equations for every single time ti in the hierarchy. Okay, so this is really a Lagrangian formalism encoding an integrable hierarchy. So all the times are described by the same Lagrangians, all the time evolutions, and it tells you also that the Hamiltonian is Poisson commute for free. Okay. And one thing that I want to do later in the Hitchin system is think about gauged Lagrangian one-forms. So this is a natural way of doing symplectic reduction in this Lagrangian framework. So let's think about having a Lie group G acting in a Hamiltonian way on the cotangent bundle with a moment map given by mu. And let me suppose that all the Hamiltonians are invariant under this symmetry, so that they Poisson commute with the components of the moment map. And then so what Hamiltonian reduction means is you restrict to the level set of the moment map equal to 0, and then you have to quotient by an extra residual gauge Lie symmetry G. So you go to this quotient, symplectic quotient mu inverse of 0 divided by G. So the point is you can implement this reduction in the Lagrangian framework very naturally. So first of all, you want to enforce the condition that mu equals 0. And this you can do by introducing a Lagrange multiplier. So because the moment map is valued in G star, the Lagrange multiplier should be valued in G so that you can pair it with the moment map. So you get this extra term. So you have the Lagrange multiplier A times the moment map. So this will enforce through the equations of motion for A the condition that mu equals 0. And I note here that this is a one form because I'm modifying a Lagrangian one form. Mu is a scalar function, so I need A to be a one form. So it's a one form field on Rn, the multi-times, valued in G. And then to pass to the quotient, what you have to do is just, you realize that once you've added this gauge field, or this one form field to the action, the global G symmetry gets promoted naturally to a gauge symmetry. So you can act with the gauge group of all smooth functions from Rn to G. You can act pointwise on the map sigma, so on the P's and Q's. And you let this one form field A transform as a gauge connection. Okay, so through this procedure, this one form field gets promoted to a gauge field along Rn. This will be very important to remember for later. So we have a connection along Rn from the process of gauging the one form. Okay. So you can derive the equations of motion in the same way as before. The new equation is just the variation with respect to the Lagrange multiplier, which, as we said, just gives you the constraint mu equals 0. The other equations are, of course, a bit modified, so they describe a constrained Hamiltonian system, where now the dynamics is not induced just by the Hamiltonian H itself, but also the Hamiltonian plus an arbitrary function of time times the constraints. So this is essentially implementing a gauge transformation along the flow at every instant in time. This A tilde is technically just the one form, but written in the coordinate t. Remember that in the previous ungauged setting, I had to invert the matrix dti by duj. I have to do it here as well, and this produces this new connection A tilde in the t coordinate. And the other nice thing is that if the action of G is invariant, is free, then these A's here actually describe a flat connection on space. On the space Rn. And I forgot to say, crucially, again, we still have the involution property. This comes out just for free from varying with respect to the times ti. Okay. Are there any questions up to this point? Okay, so now I want to pass to the Hitchin system and remind you in what sense it's a completely integrable system, and then apply all this machinery to that system to produce a 3dBF theory. So Hitchin system is an integrable system where the spectral parameter lives on an arbitrary Riemann surface G. And I'll take this genus to be 2 or more for simplicity in this talk. We can also treat the case of 0 and 1 in the paper. These are degenerate cases, so I don't want to focus on them too much for uniformity. So the phase space of the Hitchin system is given by the cotangent bundle of isomorphism classes of stable holomorphic principal bundles on the Riemann surface C. So this is a mouthful. If you don't understand all these words, I'll explain how to think about this on the next slide. The key point is that this is actually a finite dimensional space. And so the cotangent bundle of this manifold, in fact, it's a manifold, and the cotangent bundle of it is a finite dimensional manifold which has dimension 2 times the genus minus 1 times the dimension of the Lie algebra. And why this is, first, to describe the Hamiltonian system, you need to give Hamiltonians. And in fact, Hitchin gave a family of Hamiltonians, which is a complete set of Hamiltonians, through what's called the Hitchin fibration, or the Hitchin map. So this is a bit involved. The way you define these Hamiltonians is as follows. So you want to define functions from the phase space to the complex numbers. So first you define a map from phase space to some space of sections of some sheaf, of some bundle. The way you do this is think about the fiber at any point above a isomorphism class of holomorphic principal bundle. So you pick a holomorphic principal bundle, and then above this bundle there's a fiber, and this fiber is canonically isomorphic to what's called the Higgs fields. So these are holomorphic 1-0 forms valued in G star. So I call them B in this talk, usually it's called phi. So these are parameterizing the fiber of the cotangent bundle above a point in the base. So these are the Higgs fields, holomorphic Higgs fields. And so the idea of the Hitchin fibration is to pick a basis of homogeneous polynomials in the, on the dual of the Lie algebra G. So they're labeled by 1 to the rank of G. And their degrees as homogeneous polynomials are given by the exponent of the Lie algebra plus 1. So you take these polynomials on G, you apply them to the Higgs field, which is valued in G star. So the polynomials are on G star, so you can apply them to the Higgs field. So you get these sections of these powers of the canonical line bundle. And so these are not yet complex valued Hamiltonians, they're valued in this weird space of sections. But the point is this is a finite dimensional space of sections, so you can then pick a basis of that space. And the coefficients in that basis give you Hamiltonians from the cotangent bundle to the complex numbers. So the point is these are finite dimensional spaces of sections with these precise dimensions, and you can extract from the coefficients in a basis individual Hamiltonians. And the remarkable fact is that the dimensions of these spaces, when you add them up, it turns out to be equal exactly to half the dimension of your phase space. So this is why the Hitchin system is completely integrable. The number of Hamiltonians that you build, which are independent, they coincide with half the dimension of the phase space. Okay. So for our purposes, to be able to connect to the 3dBF theory, we need to use the fact that the Hitchin's phase space can be described in a slightly different way, which comes from the fact that you can think about holomorphic principal bundles in a different way. So holomorphic principal bundles are principal bundles where the transition functions are holomorphic. But you can start with a smooth principal bundle, so where the transition functions are smooth. And you can think about the space of G-valued 0-1 connections on this principal bundle. So concretely, what these are described by is in every open patch on the base C, on the Riemann surface C, you prescribe some 0-1 forms valued in the Lie algebra G, and they should connect with each other over intersections through gauge transformations by the transition function. So this is what it means to have a G-valued 0-1 connection on the principal bundle. Okay, so the point is any such 0-1 connection, it defines a unique holomorphic structure on the principal bundle. Why? Because I can always move locally to a local trivialization where the components of A double prime is actually 0. So I can gauge away this A double prime. And in that gauge, if A double prime is 0, in this equation you can see both the left-hand side and the first term on the right are 0. So that tells us that the transition function will become holomorphic. So that's why if you give me a 0-1 connection, I can construct a holomorphic structure on the principal bundle because I can choose a local trivialization where the transition functions become holomorphic. And if you give me two such 0-1 forms, then actually they define isomorphic holomorphic structures if and only if they are related by a bundle automorphism. So by a gauge transformation, So bundle automorphisms are these things that act on the connections by gauge transformations. Okay, so that means that I can think about holomorphic structures on the principal bundle as 0-1 connections, but I have to remember to mod out by gauge transformations by the automorphisms of the bundle. So I take this space M of this affine space of G-valued connections. I mod out by the group G of automorphisms of the bundle. This gives me the base of the Hitchin phase space, the space of isomorphism classes of holomorphic bundles. And the nice thing is that this action of the automorphism group on the space of 0-1 connections lifts to the cotangent bundle. So you have a Hamiltonian action of the automorphisms of the principal bundle on the cotangent bundle, and this is a Hamiltonian action with moment map given by this nice formula. So it's valued in the dual of the Lie algebra of the space of automorphisms, of the group of automorphisms of the principal bundle. So just to explain what this formula means, because it will be important in a second, remember that I can think of Higgs fields as elements of the fiber of the cotangent bundle above a point on the base. So here, because I'm now working with smooth principal bundles, my Higgs fields are smooth sections of that same bundle I had before. So they are smooth 1-0 forms valued in G star. Concretely, this means that they are just 1-0 forms valued in G star on every patch. And this is the associated bundle to the principal bundle in the adjoint representation. That just means that on different patches, they relate by the co-adjoint action. The Lie algebra is described in a similar way. So it's global smooth sections of the adjoint bundle, and that means that I can describe them locally by smooth functions on every patch valued in G, which transform across patches by the adjoint action. The covariant derivative del bar A double prime just means taking covariant derivative of this Lie algebra element X. And because it's covariant, I still get something transforming in the adjoint representation. So it's a 0-1 form because I took the del bar derivative. And so I can now pair the covariant derivative of the vector of the Lie algebra element, which is a 0-1 form, with the Higgs field. Because they transform in adjoint and co-adjoint representations, they actually pair nicely to form an invariant section over the whole manifold, and I can integrate it over the manifold. So this moment map, if you do the Hamiltonian reduction of the action of G with respect to this moment map at level 0, you get precisely the cotangent bundle of the space of holomorphic principal bundles on G. So this is the phase space of the Hitchin system. I'm telling you that there's an alternative nice description as a symplectic reduction. And this is exactly what we need to apply the machinery I told you about in a second ago, that you can start with a Lagrangian one form on the cotangent bundle, which has this action of G. Provided the Hamiltonians are invariant, we'll be able to gauge this Lagrangian one form to produce Lagrangian one form describing the dynamics on this reduced symplectic manifold. So this is exactly what I want to do now, construct a Lagrangian one form on this cotangent bundle. So I wanted to produce the Hitchin system in the end, so the choice of Hamiltonians to describe the dynamics on this cotangent bundle will be guided by the Hitchin construction. So remember the Hitchin fibration, which took a holomorphic Higgs field and produced, and you apply these polynomials to this holomorphic Higgs fields to produce the sections of these holomorphic bundles. And then because I had the basis, I could choose a basis of these spaces, I could just pick out the coefficients in that basis. Now I'm dealing with smooth principal bundles. And as I said, the fiber of this cotangent bundle is now smooth Higgs field. So I can still apply the polynomials that we chose for the construction of the Hitchin map. I can still apply those polynomials to the smooth Higgs field, but I get smooth sections of the same bundles. So I can no longer decompose them into a basis of holomorphic sections because they're smooth. Instead, what I do is I just pick a set of points on the curve and evaluate these polynomials at those points. And you can show that this choice, it provided the set of points as a generic divisor on the curve. This procedure will land back exactly on the previous prescription for the construction of the Hitchin Hamiltonians when the B field becomes holomorphic. So I'm defining a construction here of Hamiltonians on the lifted phase space T star M, which will reduce down to the Hitchin Hamiltonians when you pass to the holomorphic description. So these Hamiltonians are just given by taking the Higgs field, which is smooth, evaluating it at a bunch of points, and then plugging this into the invariant polynomials. So these are my collection of Hamiltonians. There are still n of them because I chose the bunch of points Q to be n in total. So there are n Hamiltonians. Okay, and then the Lagrangian one form is easy to write. So it's just P dq minus the Hamiltonians. So the coordinate along the fiber of the cotangent bundle is B, the Higgs field. And so that's P. And then dq, Q is the coordinate along the base. It parameterizes the 0, 1 form on the base. So P delta A double prime is P dq minus the Hamiltonian. So this is just a very canonical Lagrangian one form describing the dynamics of these Hamiltonians on that phase space. Okay. So I want to play the same game as before and introduce some gauge fields. So first of all, remember to write down the action, the multiform action. I need to make a choice of immersion, which describes the n-time dynamic of my fields in the cotangent bundle. So I pull back the Lagrangian one form along this immersion, and I get this object, which is a Lagrangian one form on Rn now. And to gauge it, what I do is, so first of all, I can gauge it because my Hamiltonians are invariant under the adjoint action of the bundle automorphisms. So that means that I have an invariant action under this symmetry group. So I can gauge it by adding the moment map paired with a Lagrange multiplier in the same way as I showed you before in the finite dimensional setting. So remember that this is the Lagrange multiplier is a G-valued connection on so along Rn. So now it has this extra dependence on the spectral curve. This is just because I'm dealing with now the Hitchin system where the Lie algebra is really, the Lie algebra is functions from C to the Lie algebra little g. And so there's an extra C dependence in my gauge field. So it's really a gauge field on C cross Rn, which is a connection along Rn. So it has only components along Rn. But the remarkable thing is that if you expand out what this sigma pool L is, you get the kinetic term, which combines very nicely with this moment map term. So I've written out here the moment map explicitly. It's B d bar A double prime acting on A. And these two terms combine very nicely to form the BF action. So in particular, the original 0-1 connection, which describes holomorphic structures of the bundle P, they combine with the one-form connection that describes the gauging to the level mu equals 0. They combine to a connection on C cross Rn, which has all directions now holomorphic along C and all the directions along Rn. So it's full connection. And its curvature pairs with the field B. So this is the BF action, which emerges very nicely from this construction just by gauging the canonical action on the cotangent bundle. So I should say this is really a multiform version of the 3D mixed BF action, which, as we'll see, describes all the dynamics of the hierarchy of the Hitchin Hamiltonians. Okay, so here this is really a description of the Hitchin system. It's a full description of the Hitchin system, but in terms of smooth data, because the B field is a smooth Higgs field, the curvature or the connection A is a smooth connection, and really the Hitchin system to start with was described in terms of holomorphic things, a holomorphic Higgs field and a holomorphic principal bundle. So I can use the fact that I can always pass to this holomorphic description. Remember that the choice of a 0-1 connection is equivalent to the choice of a holomorphic structure. So what I can do is I can think about a way of trivializing the principal bundle with its holomorphic structure. So let's fix a point P on the curve and a neighborhood U0 of the point. And then U1, which is a complementary open, is just the entire curve minus a point. So the claim is that the holomorphic principal bundle P with its A double prime, which describes the holomorphic structure, it's actually holomorphically trivial on both opens. So on U0, this is because U0 is a small open and it's locally trivial. And on U1, this is because there's this deep fact that holomorphic principal bundles on non-compact Riemann surfaces are always trivializable. So my holomorphic principal bundle is trivializable on both of these opens, U0 and U1. So that means that I can move to local trivializations in both of these patches where the holomorphic structure A double prime is equal to 0. Okay, and remember what that means is that in that local trivialization, the transition functions between the two patches are given by holomorphic functions. So really here they're holomorphic along C. There's an extra Rn dependence that's creeped into the story because of this gauging procedure. But really what I have is a bundle living on C cross Rn, which is a principal bundle with group valued transition functions, and they're now holomorphic in this choice of trivialization. And what I also want is the gauge field, or the Higgs field to be holomorphic. And I can achieve that by imposing the constraint mu equal to 0, because mu, remember, is this constraint. And so if I set it to 0, I'm really saying that in the gauge A double prime equals 0, I'm saying just del bar B is 0. So B becomes holomorphic. Okay, so I'm now dealing with a holomorphic transition function for my bundle. So it's really a holomorphic principal bundle. And the Higgs field, which parameterizes the fiber, is now holomorphic by solving this constraint mu equal to 0. So it's given by two holomorphic functions on a patch U0 and U1, which are connected together by these holomorphic transition functions on the intersection. Okay, so now I can derive the action for this in this holomorphic description. So this is a non-trivial statement. So I claim that if you start with a 3dBF action that I showed you before, and you move to this holomorphic description where the gauge fields, or the transition functions become holomorphic, and the Higgs field becomes holomorphic, then the action turns into the following. So the BF term becomes this piece. And the reason it's non-trivial is because here you have transition functions appearing, which are living on intersections of patches, whereas before I just had a pairing between the B field and the gauge field, which were living on opens themselves. So there's a non-trivial step happening here, and you can read more about it in our paper. But this is the result of the reduction to this holomorphic picture. And what's really nice is if you derive the equations of motion for this action, which is again quite non-trivial, well, for the different fields in the action, you get the following. So first, varying the action with respect to L, you get the existence of some G-valued function on the open U, and a meromorphic G-valued function on U1 with simple poles at the QIs. So QIs were the points where I inserted the Hamiltonians, which I used to construct the Hamiltonians. So these meromorphic and holomorphic functions valued in G, they're connected on the overlap by these gauge transformations by the holomorphic transition functions. And if you vary the action with respect to the transition functions, you get the Lax equation for the Higgs field. So this is really the Hitchin equation written in Lax form. So it tells you that the evolution of the Higgs field with respect to all the times is governed by the Lax equation, which is the commutator of these matrices M with the Lax matrix, or the Higgs field. And this is true in both patches by virtue of this transformation property of these M's. Again, as usual, the variation with respect to the times gives you the involution property of the Hamiltonians. So it's really rebuilding the whole Hitchin system. And the stability condition that I assumed about the holomorphic principal bundles, they lead to this condition that the matrices which emerge from the variation with respect to L, they form a flat connection on multi-time space. And this is a key property of these integrable systems or integral hierarchies, that the matrices M which appear in the Lax connection, or in the Lax equation, they should form a flat connection on multi-time space. So this is really the equations of motion for the Hitchin system formulated in the Lax formalism, which are derived from this action. So let me summarize, because I'm out of time. So what I showed you is how to derive a variational formulation of the full Hitchin system, namely the whole hierarchy of the Hitchin system, by starting with a very canonical action on the cotangent bundle of the space of 0, 1 connection on a smooth principal bundle, gauging this action by noticing that it's invariant under the action of the bundle automorphisms. I gauge this action to get the 3dBF action. And then, so this describes the Hitchin system already, but in terms of smooth data, so smooth Higgs fields and smooth bundles. Then I can pass to the holomorphic description to get a description of the Hitchin system in its original description in terms of holomorphic data. We can also generalize all of this to Riemann surfaces of genus 0 and 1. And we can also add extra marked points where the Higgs field is allowed to have poles. So we get meromorphic lax connections. And we can produce very explicit examples of rational and also elliptic Godin models. And so this is the genus 1 case and the elliptic spin Calogero-Rimoso model as a special case. So natural questions which follow from this work is, can we use this Lagrangian formulation of the Hitchin system, specifically of the whole hierarchy, to possibly quantize the hierarchy of the Hitchin system by using possibly some path integral methods extended to the multiform setting? It would be very nice to figure out if what I told you today generalizes to these high dimensional settings. So can we find, for example, multiform versions of the 4D, 5D, 6D Chern-Simons actions and derive from that some multiform versions of the Lagrangian formulations of these integrable hierarchies in 2, 3, and 4 dimensions. And also, all of this worked for higher genus Riemann surfaces. So the natural question is, can you extend also the construction in higher genus in a similar way to what we've done to higher genus in higher dimensions? Okay, thank you.
Thank you very much for your talk. Nice talk. Do we have some questions? In the back. There's another one first. Okay, so you're number 3.
I had a question if you have an idea on about how to embed in string theory this construction, if you have intuition of it.
So I'm afraid, yeah, my talk was not at all about string theory. I mean, I know that there are ways of embedding 4D Chern-Simons into string theory. I think there's also 3D. So Gayoto-Witten did some work, I think, on how to embed 3D mixed BF into string theory. So there's work on this. I'm just not very familiar with it. You can, I think, do this. Yeah.
Okay.
There was a question. Sergey had a question, and then Arkady had a question.
I have a couple of questions. Is there an integrable deformation of Hitchin system to the case where the phase space is a Heisenberg double?
Is there what?
Integrable deformation of Hitchin system.
Where the phase space is what, you said?
The Heisenberg double. Not the cotangent bundle, but...
Yeah, that's a good question. I haven't thought about it. Yeah.
And can you also consider elliptic spin Roegenar-Snyder model?
Is it a Hitchin system?
No, it's...
Okay. So we haven't thought about it, but it's a natural question. The question is, can you describe it from 3dBF? I'm not sure because...
Think about it as a deformation of elliptic spin Calogero.
Yeah, okay, as a deformation, yeah.
And it's a relativistic invariant, it has a relativistic invariance.
Yeah, these are all very natural questions I don't know the answer to. I haven't thought about them. Yeah, we can discuss them.
So very naive question. So Hitchin system you can get from self-dual Young-Mills by reduction. Is there any implications for self-dual Young-Mills? Because you can get self-dual Young-Mills from BF systems as well.
Yeah.
You can uplift it further.
So I think in all these stories, if you go higher in dimensions, you get broader and broader classes of integrable systems, which can then reduce down to the systems you get from lower dimensional theories. So 3dBF is at the very bottom. So probably you can get it from reduction of, what did you say? Is it 60 holomorphic Chern-Simons or? Four-dimensional? Yeah, so 4-dimensional BF would be, I think, a special case or a special limit of 4D Chern-Simons. Holomorphic 4D BF is a special limit of 4D Chern-Simons. And then there's a reduction, which is quite natural to 3D BF theory. So maybe there's a link to.
Do you expect that quantizing the Hitchin system would be equivalent to quantizing this 3D theory?
Yeah, that's a good question. That's the kind of question that we want to address. It's a very simple setting compared to 4D Chern-Simons, so it's a natural setting to start addressing these questions properly. Yeah. So the system you're dealing with is finite dimensional. the 3dBF theory is a lot simpler than 4D Chern-Simons. So yeah, you can play the same games that you like to play, but in this one-dimensional less. And it's a natural question. Yeah, the question you ask is quantizing the Hitchin system the same thing as quantizing 3dBF? You could try to answer this question. We don't know yet.
Thanks.
Yeah.
So thank you for the nice talk. There is a relation between Hitchin moduli spaces and four-dimensional theories with n equal to 2 supersymmetry, which was explored by this work by Gaiotto, Moore, and Neitzke about a decade ago. And they led to a relation with integrability, and in particular, there are thermodynamical Bethe ansatz type of coordinates on the moduli spaces of the Hitchin system.
Yeah.
Do you have a comment? Is there a relation that does this construction that you have by something in the direction? Or?
It's a very good question. I haven't thought about it. So the point is Hitchin appears in many different contexts. That's one of them. So it's natural to explore whether this has anything to say about that story. Yeah, it's a great question. We can discuss it. Yeah.
So my question is a little bit twofold. One is attached to his question. I think that what is talking more naturally is the higher dimensional, four-dimensional Hitchin system, because this is the case of GMN, as far as I can understand. So you are dealing with a reduction. You are doing something in 3 dimensions. So you should get some reduction of the GMN space, possibly, if something works. Is that correct?
Yeah, but I thought Hitchin system appears directly in the GMN construction, maybe through a reduction, but it's certainly there explicitly. So I think there should be a link to 3dBF as well, not only through 4D Chern-Simons. Yeah.